In this video, I'm going to show how to derive the formula for the Taylor series. So first of all, let's assume that f of x, function of x, has a power series representation in the form of, sigma from n equals 0 up to infinity of a sub n times x minus c to the n. So that's just the basic form of a power series. So expanding this, we get a sub 0 by plugging in 0 for n, plus a sub 1 times x minus c plus a sub 2 times x minus c squared. I'm just going to do a couple more. A sub 3 times x minus c cubed plus a sub 4 times x minus c to the fourth, and I'll do one more, plus a sub 5 times x minus c to the fifth, and so on. Okay, so here we have an expanded version of this power series. So our goal is to basically find a formula or an expression for this a sub n. We want to find out a specific formula for a sub n. So goal is to find a sub n. So how I'm going to go about doing this is basically I'm just going to start taking derivatives of f of x. So let's start off with f prime. So f prime of x equals, well, the a sub 0 is going to go away, and then we're basically just applying the power rule term by term. So f prime of x is going to equal, well, a sub 1 plus, and then applying the power rule, we get 2 a sub 2 x minus c plus 3 a sub 3 times x minus c squared plus 4 a sub 4 times x minus c cubed plus 5 a sub 5 times x minus c to the fourth, and so on. And you'll see in a little bit why I chose to expand out to 5 terms. It will be needed to find a pattern in a little bit, a couple steps. So essentially, I'm just going to keep taking derivatives. So let's calculate f double prime of x. So that's going to be, so the a sub 1 is going to go away. So we're just going to get 2 a sub 2 plus, so bring the 2 down, multiply it by the 3, we're going to get 6 a sub 3 times x minus c plus, so 3 times 4, that's 12, a sub 4 times x minus c squared plus 4 times 5 is 20, so we have 20 a sub 5 x minus c cubed. And I'm going to take a couple more just until I get to this term as just the constant term. So we'll do f triple prime of x is 6a cubed plus 12 times 2 is 24. 24 a sub 4 x minus c. 3 times 20 is 60. So plus 60 a sub 5 x minus c squared. All right. Looks like 2 more derivatives should just about do it. So we'll do the fourth derivative of x is, well, 24 a sub 4 plus 60 times 2, well, that's 120. So 120 a sub 5 times x minus c. And one more, so the fifth derivative of x is equal to, well, just 120 a sub 5. All right. So why did I just take all these derivatives? Well, now notice if we evaluate, so if we evaluate f of x, f prime of x, f double prime of x, if we evaluate all these functions at the special point where x is equal to c, if you notice, so in f of x, if we plug in x equals c, from this term all the way on to infinity, every term is 0. Same with here. Every term starting from the second term will be 0. So basically, if we plug in x equals c, every single term goes to 0 except for the very first term, which is the constant term. This one, this one, this one. So that's what I'm going to do. So I'm going to say, so I'm going to start with f of x. I'll just write it down here first. So f of c equals, so basically when I plug in c, like I said, it's just going to be the first term in all these equations. So f of c is just going to be a sub 0 from right here. So a sub 0. F prime of c, again, is just going to be the first term in that equation. So it's a sub 1. And start seeing a pattern pretty quickly. F double prime of c is just a sub 2. Well, 2 a sub 2. 2 a sub 2. That's from right here. And then f triple prime of c is equal to 6 a sub 3. And then, let's see, 2 more. So the fourth derivative evaluated at c is 24 a sub 4. And then finally, the fifth derivative evaluated at c is equal to 120 a sub 5, right here. 120 a sub 5. Okay, so now here comes a little, you just got to notice the pattern. So basically, right here, there is a 1 being multiplied there, 1 being multiplied there. So essentially, f of c equals 1 times a sub 0. F prime of c equals 1 times a sub 1. So it goes 1, 1. I'm talking about the coefficients here. It goes 1, 1, 2, 6, 24, 120. So if we relate that number to the number of derivative, so what that means is, so f of c, that is technically the 0th derivative, right? We didn't take any derivatives. So we could say that f of c also equals 0 factorial times a sub 0. Because 0 factorial is defined to be just 1. So then f prime of c equals 1 times a sub 1. That can be written as 1 factorial times a sub 1. Obviously, 1 factorial is just 1. By the way, factorial, the generic form, so n factorial is just equal to n times n minus 1 times n minus 2, all the way down to 3 times 2 times 1. It's basically just multiplying every integer starting from the integer you have down to 1. Okay, so 2 can be expressed as, well, 2 factorials, just 2 times 1. So 2 factorial a sub 2. And then 6 is actually 3 times 2 times 1. So it's 3 factorial a sub 3. And here we start seeing the pattern. This 3 factorial here, third derivative here. 2 factorial here, second derivative here. So fourth derivative here, we should get a 4 factorial. And 24 is 4 factorial, right? We have 4 times 3, which is 12, 12 times 2, which is 24, times 1. So this can be rewritten as 4 factorial a sub 4, and then this is 5 factorial. 120 is 5 factorial. So 5 factorial a sub 5. And now here's the jump. If we have the fourth derivative, 4 factorial a sub 4, fifth derivative, 5 factorial a sub 5, we should be able to make the jump and say, well, if we take the nth derivative, right, evaluated at c, that should be equal to n factorial times a sub n. So our goal, remember, is to find a formula for a sub n. Well, now we have generalized the nth derivative of the function evaluated at c is n factorial times a sub n. So now we can just divide both sides by n factorial, and we get that a sub n is equal to the nth derivative evaluated at c divided by n factorial. So that is our formula for a sub n. So now coming back up here, right, this formula, we can substitute that back in for a sub n now. So we can say that f of x is equal to the sum from n equals 0 up to infinity of not a sub n anymore, but this expression that we just derived. So that would be the nth derivative evaluated at c divided by n factorial, and then still multiplied by this x minus c to the n. And there we have it. This is the formula for the Taylor series. So Taylor series. Okay, well, let me just finish with one very quick and definitely the easiest example. Let's consider the function e to the x. Well, f of x equals e to the x. So let's try to come up with a formula for its Taylor series expansion. And I'm going to select at the point c equals 0, so centered at 0. And by the way, a Taylor series where, I'll write that over here real quick. Taylor series where c equals 0 is a Maclaurin series. So a Maclaurin series is a Taylor series, just with c equals 0. Maclaurin series. So essentially what I'm saying is let's find the Maclaurin series for e to the x. Well, we need a couple things. I guess we only need one major thing, and that is we need a general expression for the nth derivative at c. So we basically just start by taking a couple derivatives until we start seeing a pattern. Fortunately, e to the x is definitely the easiest because, so if f of x is ex, e to the x, well, f prime of x is just e to the x. F double prime of x is just e to the x. And pretty safe to say that if we take the derivative n times, we're just going to get e to the x. It never changes. So if we want the nth derivative evaluated at 0, because our c is 0 in this case, that is just e to the 0, or simply 1. So now plugging into our formula, we can say that e to the x has a Maclaurin series expansion in the form of, well, sigma starting from n equals 0 to infinity, and then f, the nth derivative evaluated at c, we just figured out is just equal to 1. So 1 over n factorial times, well, x minus c, well, our c is 0, so this is just x to the n. And just putting that in just a slightly more compact form, we have e to the x equals the sum from n equals 0 to infinity of x to the n over n factorial. And that is the series expansion for e to the x. We can expand it just a little bit. So if we plug in 0, we're getting x to the 0, which is 1 over 0 factorial. Well, that's 1. So we're just getting 1 plus, plugging in 1, we're going to get x over 1 factorial, which is just x. So plus x squared over 2 factorial plus x cubed over 3 factorial, and the pattern just keeps on going. And there we go. That was the derivation of the Taylor series formula.